Welcome to the Deep Sleep Discoveries channel. Settle into comfort now and let your breathing slow as we journey together into the deepest mysteries of the cosmos. Tonight, we explore black holes, those enigmatic regions where gravity becomes so intense that even light cannot escape, where space and time bend in ways that challenge everything we think we know. These objects represent both an ending and a beginning, a place where stars meet their fate and where the universe reveals its most profound secrets. Let yourself drift peacefully as we discover 100 gentle truths about these cosmic wonders. Before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, please consider liking and subscribing to the channel. It helps others find their way here too. Black holes form when massive stars collapse under their own gravity at the end of their lives, creating the most extreme objects in our universe. This collapse represents one of nature's most dramatic transformations, where a blazing sphere of plasma becomes an invisible region of warped space-time. The process is irreversible, marking the final fate of the universe's largest stars. For billions of years, these stars burn brightly, fusing elements in their cores, but when their fuel exhausts, gravity takes over with swift and absolute authority. The star that once pushed outward with the pressure of nuclear fusion can no longer resist the inward pull of its own mass, and in those final moments, something remarkable happens. The core begins its journey toward becoming a cosmic abyss that will exist for eons to come. A star must begin its life at least 20 to 25 times the mass of our Sun to eventually create a black hole, though it will lose much of this mass over its lifetime through powerful stellar winds and eruptions. This initial mass requirement ensures that even after the star sheds its outer layers, enough material remains in the core to overcome the forces that would otherwise create a neutron star. Not every massive star becomes a black hole. Some end their lives as incredibly dense neutron stars instead, held up by quantum pressure between neutrons. The threshold between these two fates is precise and unforgiving. Stars just below this mass limit will never quite achieve the conditions necessary for black hole formation, while those above it are destined for this transformation, and this distinction connects directly to what remains after the violent finale. For a stellar core to become a black hole after a supernova explosion, it must retain at least 3 solar masses, a threshold known as the Tolman-Oppenheimer-Volkoff limit, named after the physicists who calculated this boundary. Below this mass, even the collapsed core of a dead star can be supported by neutron degeneracy pressure, the quantum mechanical effect that keeps neutrons from occupying the same space. Above this limit, no known force in nature can prevent further collapse. Gravity becomes absolutely dominant, crushing matter beyond the point where atoms or even neutrons can maintain their structure. This limit represents a fundamental dividing line in cosmic evolution, separating objects that can achieve equilibrium from those doomed to collapse into singularities. The precision of this boundary reveals how finely tuned the universe's laws are and how swiftly nature transitions from one state to another. The star's core compresses to a point called a singularity, where matter is crushed into a space so small that our current laws of physics can no longer describe what happens there, marking the limits of human understanding. According to Einstein's general relativity, this compression should continue until density becomes infinite, yet most physicists believe this mathematical infinity signals not reality, but rather the breakdown of our theories. Quantum mechanics suggests that nature abhors true infinities, hinting that some yet undiscovered physics must take over at these extreme scales. The singularity represents not just a physical object, but a boundary of knowledge itself, a place where our most successful theories admit their own limitations. What actually exists at this point remains one of the deepest mysteries in physics, waiting for a theory that can unite gravity with quantum mechanics to reveal its secrets. The collapse happens in less than a second, one of the fastest transformations in the universe, releasing more energy in that brief moment than our Sun will emit in its entire 10 billion year lifetime. Supernova explosions often accompany black hole formation, scattering elements across space in a brilliant display visible across millions of light years. This explosion creates all the elements heavier than iron in the periodic table, from the gold in rings to the uranium in Earth's core. The outer layers of the star are blasted outward at speeds approaching 1/10 of light speed, while the inner core implodes in the opposite direction, compressed by gravity into an increasingly smaller volume. These two simultaneous movements, explosion and implosion, represent one of nature's most violent contradictions, beauty and destruction unified in a single cosmic event that seeds future generations of stars and planets. Not all black holes form from stars. Some formed in the early universe when conditions were dramatically different from today, during an era of extreme density and temperature. These primordial black holes may have emerged from random fluctuations in the fabric of space itself, regions where matter happened to be slightly more concentrated than elsewhere. In the first fractions of a second after the Big Bang, before stars even existed, the universe was hot and dense enough that gravity could amplify these tiny variations into collapsed regions. Unlike stellar black holes, primordial black holes could have formed with any mass, from microscopic to millions of solar masses, depending on the size of the original fluctuation. Though theoretical, their existence would explain certain cosmic mysteries and connect the very smallest scales of the early universe to the largest structures we observe today. Primordial black holes may have formed from density fluctuations moments after the Big Bang, when the universe was less than a second old and filled with pure energy gradually cooling into matter. These fluctuations were quantum in nature, tiny ripples in the fabric of space-time that became stretched to cosmic scales during the period of inflation. Where these ripples peaked, matter concentrated just enough that gravity could compress it beyond the point of no return. Unlike the violent supernova-driven formation of stellar black holes, primordial black holes would have formed quietly in the smooth, hot plasma of the infant universe. Some scientists propose these ancient black holes could account for dark matter, the invisible substance that makes up most of the universe's mass, though this remains unproven and represents one of cosmology's most intriguing possibilities. The smallest theoretical black holes could be smaller than an atom, tiny enough to pass through your body without you ever noticing, yet containing significant mass compressed into an impossibly small volume. These microscopic black holes would be primordial in origin, since no known process today could create something so tiny. Their event horizons might span only a few Planck lengths, the smallest meaningful distance in physics, where quantum effects dominate completely. At such scales, the distinction between classical gravity and quantum mechanics dissolves entirely, and our current theories offer only hints about their behavior. If they exist, these tiny black holes would evaporate almost instantly through Hawking radiation, flashing out of existence in bursts of energy before they could interact meaningfully with ordinary matter, creating a cosmic population invisible to our instruments. Stellar mass black holes typically range from 5 to 100 solar masses, representing the collapsed cores of the universe's most massive stars that have completed their life cycles. These are the black holes that form through the supernova process, born from iron cores that can no longer generate energy through fusion. The lower limit of 5 solar masses ensures that gravity overwhelms all opposing forces, while the upper limit reflects the maximum mass that can accumulate in a single stellar core before instability sets in. Most stellar black holes in our galaxy likely fall toward the lower end of this range, between 5 and 20 solar masses, while the heaviest stellar black holes challenge our understanding of stellar evolution. These intermediate-sized cosmic entities bridge the gap between objects formed from stars and the much more massive black holes that lurk at the centers of galaxies. Intermediate black holes exist between stellar and supermassive types, containing hundreds to hundreds of thousands of solar masses, though they remain remarkably elusive and difficult to confirm observationally. Scientists have found only a handful of convincing candidates for intermediate black holes, despite searching globular clusters and the outskirts of galaxies where they might hide. Their formation mechanism remains unclear. They might grow from stellar black holes that repeatedly merge and accumulate mass, or they could be primordial black holes that formed in the early universe. Some might represent the seeds that eventually grow into supermassive black holes, capturing gas and merging with other black holes over billions of years. Their rarity makes them precious clues to cosmic evolution, potential missing links in understanding how supermassive black holes came to exist in nearly every large galaxy we observe. Every large galaxy likely contains a supermassive black hole at its center, a cosmic anchor around which hundreds of billions of stars orbit in a vast gravitational dance that spans hundreds of thousands of light years. This relationship between galaxies and their central black holes appears to be fundamental rather than coincidental, with the black hole's mass closely correlated to properties of the surrounding galaxy. The discovery of this connection surprised astronomers, suggesting that black holes and galaxies grow together through cosmic time, each influencing the other's development. Jets and radiation from actively feeding black holes can regulate star formation throughout the galaxy, while the galaxy funnels gas and stars toward the central black hole, feeding it over billions of years. This intimate relationship suggests that understanding galaxies requires understanding their supermassive black holes, two components of a unified system that has evolved since the universe's youth. Our Milky Way's central black hole is called Sagittarius A star, pronounced a star, named for its location in the constellation Sagittarius and the bright radio emission it produces from infalling material that spirals around it. This name was assigned by radio astronomers who first detected its radio signature in the 1970s, though decades would pass before scientists confirmed it was indeed a black hole. Sagittarius A sits approximately 26,000 light-years from Earth, hidden behind dense clouds of dust that block visible light but allow radio waves and X-rays to pass through. For most of its existence, this black hole feeds quietly, occasionally flaring when a gas cloud or asteroid ventures too close. Its relatively calm demeanor today contrasts with the violent feeding frenzies that likely characterized its youth when the galaxy was forming and material was more abundant. Sagittarius AA has a mass of about 4 million suns, yet this entire mass would fit inside the orbit of Mercury, an almost incomprehensible compression of matter into a region smaller than our innermost planet's path around the Sun. The event horizon of our galaxy's central black hole measures about 12 million kilometers across, which sounds vast until you realize it contains mass equivalent to 4 million stars, each larger than our Sun. Stars near Sagittarius, a star, whip around it at thousands of kilometers per second, their orbits precisely tracing out the gravitational influence of this invisible monster. By tracking these stellar orbits over decades, astronomers calculated the black hole's mass with remarkable precision, observing stars complete their elliptical paths around seemingly empty space. This combination of enormous mass and relatively compact size creates a gravitational environment so extreme that space and time bend dramatically in its vicinity. Supermassive black holes can contain billions of solar masses, dwarfing even the largest stellar black holes by factors of millions and representing the most massive single objects in the universe today. These titans reside in the hearts of most large galaxies, their origins stretching back to when the universe was just a few 100 million years old. How they grew so massive so quickly remains one of astronomy's great puzzles, since accumulating billions of solar masses through normal feeding should take far longer than the available time. Some may have formed from direct collapse of massive gas clouds in the early universe, skipping the stellar phase entirely and starting with thousands or millions of solar masses from birth. Others might represent mergers of many smaller black holes over cosmic time, gradually building mass as galaxies collided and combined throughout billions of years of cosmic evolution. The most massive known black hole weighs approximately 66 billion solar masses, an almost unimaginable concentration of matter that challenges our theories of how black holes can grow so large in the universe's 13.8 billion year history. This ultra-massive black hole resides in the galaxy Messier 87, the same galaxy whose black hole provided our first direct image of an event horizon. At such extreme masses, the event horizon stretches across distances larger than our entire solar system, encompassing a region of space where, if you could somehow stand at the horizon's edge, the curvature would be surprisingly gentle. The existence of such massive black holes forces astronomers to reconsider how quickly black holes can accumulate matter and how efficiently galaxies can funnel material toward their centers. These cosmic leviathans represent the upper limits of what gravity can assemble into a single object. The event horizon is the boundary beyond which nothing can escape a black hole, not even light itself, marking the point of no return in the universe's most extreme gravitational environment. This invisible surface surrounds the black hole completely, a sphere in the case of non-rotating black holes, defining the boundary between the observable universe and a region forever cut off from the outside cosmos. The name event horizon was chosen because no events occurring beyond this boundary can ever be observed from outside, effectively making it a one-way information barrier. Nothing prohibits matter or light from crossing inward through the event horizon. It simply becomes impossible to reverse course once you've crossed. This asymmetry creates a fundamental divide in space-time, separating two regions that can never again communicate, no matter how long you wait or how advanced your technology becomes. Event horizon comes from the idea that no events beyond it can be observed, creating an absolute limit to how much of the universe we can ever see or know, even in principle. The concept parallels the cosmological horizon that limits how far we can see into the universe, but with a crucial difference. The cosmological horizon exists because light hasn't had time to reach us since the Big Bang, while the event horizon exists because gravity prevents light from ever escaping. Crossing the event horizon means permanently disconnecting from the external universe, entering a region where your future cannot influence anything outside. For an outside observer, you appear to slow down and fade as you approach the horizon, never quite seeming to cross, though from your perspective you'd sail through smoothly. This creates a strange situation where different observers fundamentally disagree about when and whether you crossed this boundary. The size of the event horizon depends directly on the black hole's mass, growing proportionally larger as more matter falls in and increasing the gravitational grip that defines this boundary. Double the mass, and you double the radius of the event horizon, a simple relationship that emerges from Einstein's equations of general relativity. This linear relationship means that supermassive black holes have event horizons millions of times larger than stellar black holes, even though their densities are actually lower. The average density inside the event horizon of a supermassive black hole can be less than water, a counterintuitive fact that demonstrates how the singularity's infinite density is concentrated at the center while the event horizon encompasses an enormous volume. This scaling relationship makes supermassive black holes surprisingly gentle environments at their boundaries, quite different from their smaller cousins. A black hole with Earth's mass would have an event horizon smaller than a marble, roughly 9 millimeters across, though creating such an object would require compressing our entire planet into a space smaller than your fingernail. This thought experiment illustrates how extreme black hole conditions really are, showing that everyday objects contain far too little mass to spontaneously form black holes under normal circumstances. Earth's gravity, while strong enough to hold our atmosphere and keep us grounded, falls far short of what's needed to prevent atoms from resisting compression. To create such a tiny black hole would require forces vastly beyond anything nature provides on planetary scales, which is why black holes form only in the collapsed cores of massive stars or in the extreme conditions of the early universe. The marble-sized event horizon would contain all of Earth's mountains, oceans, and core, collapsed to unimaginable density. The Sun, compressed to a black hole, would have an event horizon just 3 kilometers across, small enough to fit comfortably within a city, yet it would contain all the mass that currently produces light and warmth for our planet. This calculation, called the Schwarzschild radius after the physicist who first computed it, reveals how much empty space exists in normal matter since the Sun's current diameter is nearly 1.4 million kilometers. If you could somehow compress the Sun into a black hole while keeping Earth in its orbit, our planet would continue circling at the same distance and the same speed because the gravitational pull would remain unchanged. The difference would be catastrophic for other reasons. Without the Sun's light and heat, Earth would freeze, and the lack of radiation pressure would cause dramatic changes throughout the solar system. This demonstrates that black holes are dangerous not because they suck more than other objects, but because of extreme conditions near their surfaces. Supermassive black holes can have event horizons larger than our entire solar system, extending beyond the orbit of Neptune and encompassing the realm where all our planets circle the Sun. The largest black holes have event horizons that would take light hours to cross from one side to the other, compared to mere milliseconds for a stellar mass black hole. Despite their enormous size, these event horizons still represent the boundary of the black hole proper, with the singularity at the center remaining infinitesimally small. Inside such a vast event horizon, you could theoretically survive for hours or even days before tidal forces became destructive, falling through a dark void where the singularity remains far below. The gentle curvature at such enormous event horizons means crossing the boundary might initially feel uneventful, with no obvious sign that you'd passed the point of no return until you tried, futilely, to escape. The Schwarzschild radius defines the size of a non-rotating black hole's event horizon, named after Carl Schwarzschild, who solved Einstein's equations just months after general relativity was published, while serving in the German army during World War I. His solution was remarkably elegant, showing that spherically symmetric masses warp spacetime in a predictable way, creating a radius at which the escape velocity equals light speed. For any mass, you can calculate its Schwarzschild radius using a simple formula involving the gravitational constant, the speed of light, and the object's mass. If all of an object's mass is compressed within its Schwarzschild radius, it becomes a black hole from which nothing can escape. This mathematical boundary existed in the equations of general relativity from the beginning, though Einstein himself initially doubted such extreme objects could form in nature, believing that some physical process would prevent such complete collapse. Crossing the event horizon is a one-way journey with no possibility of return, even in principle, no matter how powerful your rocket engines or how advanced your technology might become in the far future. Once across this boundary, all possible forward paths through time lead toward the singularity at the center, and backward directions through time that would lead out simply don't exist within the black hole's interior geometry. This isn't a matter of insufficient thrust or energy. The geometry of spacetime itself is so warped that outward ceases to be a direction you can travel. Trying to escape would be like trying to travel backward in time, something the laws of physics forbid. The event horizon thus represents an absolute causal boundary in the universe, a place where the normal rules about being able to move in different spatial directions break down completely, transforming your future into an inevitable collision with the singularity. Time appears to slow down near the event horizon when viewed from outside, a phenomenon called gravitational time dilation that becomes more extreme as you approach the boundary of the black hole. A clock falling toward the event horizon would appear to tick slower and slower to a distant observer, its signals becoming increasingly redshifted and dim as the clock approaches the horizon. From far away, you would never actually see the clock cross the horizon. Instead, it would appear to freeze in place, fading to darkness as its light becomes infinitely redshifted. This effect isn't an illusion or a limitation of observation. Time genuinely passes at different rates in different gravitational fields, a prediction of Einstein's relativity confirmed by countless experiments with precise atomic clocks. The extreme gravity near a black hole stretches time to such an extent that infinite time passes for the outside universe during the final approach. From an outside observer's perspective, objects never quite reach the event horizon, instead appearing to slow down asymptotically, frozen in time at the boundary while fading to invisibility as their light becomes too redshifted to detect. This creates a strange paradox. From the outside, nothing ever enters a black hole, yet from the infalling object's perspective, the crossing happens smoothly and in finite time. Both perspectives are equally valid descriptions of the same physical reality, neither one more true than the other, though they appear to contradict each other. The resolution lies in understanding that space-time itself is divided into regions that cannot communicate. Once you cross the horizon, you can no longer send signals to the outside universe, so the outside observer's perception that you never crossed becomes permanent. This demonstrates how relativity doesn't just affect speeds and times, but fundamentally alters the nature of reality itself. For someone falling in, crossing the event horizon happens in finite time, perhaps just seconds or minutes depending on the black hole's mass, with no dramatic sensations or obvious markers indicating when the boundary has been passed. You wouldn't see a signpost or feel a jolt. The crossing would be smooth and, for supermassive black holes, surprisingly gentle at first. Looking back, you might still see the outside universe, though increasingly blue-shifted and compressed into a shrinking circle behind you as your velocity approaches light speed. The stars outside would appear to speed up, and you might watch the future of the universe unfold in accelerated time as you fall inward. But communication with the outside would be impossible. Your signals would never escape to reach them, while their signals to you would seem to arrive all at once, compressed into the final moments before reaching the singularity. Most black holes spin, which affects their structure and behavior significantly, creating additional features and phenomena not present in the simpler, non-rotating Schwarzschild black holes that served as early theoretical models. This rotation comes from the angular momentum of the original star, which spins faster as it collapses, like an ice skater pulling in their arms, conserving rotational motion in an increasingly compact space. A rotating black hole drags the space around it, creating a region where even light must participate in the rotation, unable to remain stationary relative to distant stars. This frame-dragging effect becomes more pronounced closer to the horizon and creates fundamentally different geometry than non-rotating black holes possess. Real astrophysical black holes almost certainly rotate, since the stars that formed them rotated, and material falling in spirals rather than falling straight down, adding even more angular momentum. Rotating black holes have two event horizons, an inner and outer boundary, with a strange region between them where the geometry of space-time becomes even more exotic than in the exterior or interior regions alone. The outer event horizon is the true point of no return, while the inner horizon separates the region between them from the ring singularity at the center. Between these horizons lies a realm where time and space behave in peculiar ways, and in principle trajectories exist that could avoid the singularity, though instabilities likely make such paths impossible in practice. The mathematical structure of rotating black holes, described by the Kerr solution to Einstein's equations, includes features like closed time-like curves that appear to permit time travel, though most physicists believe quantum effects would prevent such exotic possibilities. This double horizon structure makes rotating black holes far more complex than their non-rotating cousins, with richer physics and stranger geometry. The ergosphere is a region outside a rotating black hole where space itself is dragged along so strongly that nothing can remain stationary, forced to rotate in the same direction as the black hole regardless of any attempt to resist. This region extends beyond the outer event horizon and has an egg-like shape, wider at the equator than at the poles, reflecting how the frame-dragging effect is strongest in the plane of rotation. Inside the ergosphere, you could still escape back to the outside universe, unlike inside the event horizon, but you couldn't simply hover in place. You'd be swept along like a boat caught in a current. The boundary of the ergosphere is called the static limit because it marks the limit at which static observers can exist. This region enables the Penrose process, a theoretical method for extracting energy from rotating black holes, where particles entering the ergosphere could split in special ways. Inside the ergosphere, nothing can remain stationary. Everything must rotate with the black hole, caught in the current of dragged space-time like leaves swirling in a cosmic whirlpool that spans distances greater than worlds. Even light itself must rotate with the black hole when inside this region, unable to maintain straight trajectories relative to distant stars. The closer you get to the event horizon, the faster you're forced to rotate, approaching the speed of light at the horizon itself. This forced rotation represents one of the most striking demonstrations of how matter and energy can influence the structure of space-time itself, with the black hole's spin literally pulling the fabric of reality along with it. The ergosphere's existence suggests that space-time isn't merely a passive stage on which events occur, but an active participant in physics, capable of motion and deformation like any physical substance. Black holes have the strongest gravitational pull in the universe, creating regions where space-time curves more sharply than anywhere else in existence, warping reality itself into extreme configurations that challenge our understanding of physics. Near the event horizon, gravity becomes so intense that it dominates every other force in nature, overwhelming the electromagnetic forces that hold atoms together and the nuclear forces that bind atomic nuclei. This supremacy of gravity occurs because gravitational force has no upper limit and grows without bound as masses concentrate more densely, while other forces either reach plateaus or become irrelevant at the scales involved. Nothing in the universe can generate stronger gravitational fields than black holes, making them natural laboratories for testing gravity under the most extreme conditions imaginable. Their intense gravity warps not just the trajectories of objects but the very geometry of space and time, creating effects that seem almost magical in their departure from everyday experience. Gravity near a black hole warps space and time into extreme curves, bending the fabric of reality so sharply that straight lines become impossible and all paths lead inexorably toward the center. This warping isn't merely metaphorical. Space itself, the actual distances between points, stretches and distorts, becoming highly curved like the surface of a sphere, but in more dimensions than we can easily visualize. Time also warps, flowing at different rates at different distances from the black hole, creating situations where clocks tick at vastly different speeds depending on their location in the gravitational field. These distortions of space-time aren't separate effects, but represent different aspects of the same underlying geometry, woven together in the four-dimensional fabric that Einstein's theory describes. Near the event horizon, this curvature becomes so extreme that time-like and space-like directions begin to interchange their roles, fundamentally altering what forward in time and outward in space even mean. Einstein's general relativity predicts black holes with remarkable accuracy, describing their properties and behavior through equations he published over a century ago, long before any observational evidence confirmed these exotic objects existed in nature. The theory frames gravity not as a force but as curvature in space-time, with massive objects creating dips and warps that other objects follow, like marbles rolling on a stretched rubber sheet. Black holes represent the extreme limit of this curvature, where the warping becomes so severe that space-time essentially folds in on itself, creating a region disconnected from the outside universe. Every prediction general relativity makes about black holes, from their shadow size to the gravitational waves they emit when merging, has been confirmed by observations with extraordinary precision. This success makes general relativity one of the most well-tested theories in physics, validated across scales from GPS satellites to colliding black holes billions of light-years away. The escape velocity at the event horizon equals the speed of light, which means that since nothing can travel faster than light, nothing that crosses this boundary can ever return to the outside universe, trapped by geometry itself. Escape velocity is the speed needed to break free from a gravitational field, and for Earth it's about 11 kilometers per second, easily achieved by rockets. As you approach a black hole, the escape velocity increases, reaching higher and higher percentages of light speed until, at the event horizon, it reaches exactly light speed itself. Beyond the horizon, the escape velocity would exceed the speed of light, which is physically impossible. You can't go faster than light no matter how hard you push. This creates an absolute barrier, not because the black hole exerts some special force, but because the geometry of space-time itself provides no paths that lead outward, the definition of escape having lost all meaning. Beyond the event horizon, all paths lead inexorably toward the singularity at the center, making the collision with infinite density as inevitable as tomorrow's sunrise and impossible to avoid through any conceivable maneuver. Inside the horizon, the singularity lies not in some direction in space, but in your future, meaning that moving toward it isn't like moving toward a place, but like moving forward in time. Just as you cannot stop time from advancing, you cannot prevent yourself from reaching the singularity once you've crossed the event horizon. Every possible trajectory, every choice you might make about firing rockets or changing direction simply alters when you hit the singularity, not whether you hit it. This transformation of the singularity from a spatial location to a temporal inevitability represents one of the most profound and disorienting features of black hole geometry, fundamentally different from anything in our everyday experience with motion and destinations. Tidal forces near black holes stretch objects in a process called spaghettification, pulling them into long, thin shapes like cosmic noodles being drawn out by the difference in gravitational pull between their near and far ends. These forces arise because gravity weakens with distance, so your feet would experience stronger pull than your head if you fell feet first toward a black hole, creating tension that grows rapidly as you approach. For stellar mass black holes, spaghettification would kill you long before reaching the event horizon, tearing your body apart as the differential forces exceed what any molecular bonds could withstand. The name spaghettification may sound whimsical, but the process it describes is violent and absolute, stretching objects thinner and thinner while simultaneously compressing them from the sides like squeezing toothpaste from a tube. This effect demonstrates how black hole gravity affects not just overall motion, but creates powerful differential forces across any object with spatial extent. Spaghettification would pull you apart before you reached the singularity, likely killing any human traveler long before crossing the event horizon of a stellar mass black hole, though the exact distance at which this occurs depends on the black hole's size and your orientation as you fall. The tidal forces grow stronger as the black hole's mass decreases, because smaller black holes have more sharply curved spacetime near their event horizons, creating steeper gradients in gravitational strength across your body. For a black hole with a few solar masses, you'd be torn apart while still thousands of kilometers from the event horizon, experiencing forces that would first feel uncomfortable, then painful, then ultimately devastating as different parts of your body try to orbit at different speeds. The process would accelerate rapidly, stretching you longer and thinner while crushing you laterally, until atomic bonds could no longer hold your molecules together. This violent end represents the fate awaiting anything falling into smaller black holes, where geometry becomes enemy. For supermassive black holes, you could cross the event horizon without initially feeling extreme forces, drifting past the point of no return almost peacefully, unaware in the moment that your fate was sealed and your future irrevocably changed toward the singularity. The gentleness arises because these enormous black holes have very large event horizons with gradually changing curvature rather than sharp bends in spacetime, making the tidal forces at the horizon relatively mild. You might survive for minutes or even hours after crossing before tidal forces became destructive, falling through darkness with the stars behind you. An astronaut could theoretically cross the event horizon of the Milky Way's central black hole and feel nothing unusual at the moment of passage, with instruments required to determine when the crossing had occurred. This counterintuitive gentleness makes supermassive black holes more hospitable at their boundaries than their smaller cousins, though the ultimate fate remains the same: eventual destruction at the singularity that still waits ahead in your future. Smaller black holes create much more violent tidal effects at their boundaries, concentrating equivalent gravitational intensity into a much smaller volume and producing steeper changes in gravitational strength across short distances, making their event horizons far more dangerous places to approach. A black hole with just a few solar masses has an event horizon only a few kilometers across, meaning the curvature of space-time changes dramatically over distances comparable to human height. The tidal forces scale with the inverse cube of distance and with the inverse square of the black hole's mass, making small black holes orders of magnitude more destructive at their horizons than supermassive ones. While you might survive crossing the horizon of a billion solar mass black hole, approaching even the horizon of a 10 solar mass black hole would tear you apart violently, stretching your molecules beyond recognition. This demonstrates how black holes of different masses create fundamentally different environments despite sharing the same basic physics, with size determining whether boundaries are gentle or catastrophic. Black holes curve light itself, creating gravitational lensing effects where light rays bend around the black hole, sometimes forming multiple images of background objects or distorting distant galaxies into arcs and rings like cosmic funhouse mirrors. This bending occurs because light follows geodesics, the straightest possible paths through curved spacetime, and when spacetime itself is curved by the black hole's mass, even straight paths become curved from an outside perspective. The effect is most dramatic near the event horizon, where light can orbit the black hole multiple times before escaping or falling in, creating circular paths at the photon sphere. Einstein himself predicted gravitational lensing in his general relativity papers, though he thought it would be too subtle to ever observe. We now use it routinely to study distant galaxies and massive objects that lens light from sources behind them. Black holes create the most extreme lensing effects possible, distorting space so severely that they can bend light rays by large angles. Light can orbit a black hole at the photon sphere just outside the event horizon, tracing circular paths around the black hole in an unstable equilibrium where gravitational pull exactly matches the light's tendency to travel in straight lines. This orbit occurs at 1.5 times the Schwarzschild radius for non-rotating black holes, creating a spherical shell where light rays travel in circles. Any slight perturbation would cause photons at the photon sphere to either spiral inward toward the event horizon or escape to infinity. The orbit is unstable, like balancing a pencil on its point. Theoretically, if you stood at this distance looking tangentially, You might see the back of your own head as light circled the black hole to reach your eyes from behind, though in practice this would be impossible to observe clearly due to instabilities and other light sources. The photon sphere marks the inner edge of the black hole's shadow in astronomical images, defining the dark circle we see in Event Horizon Telescope pictures. The gravitational redshift near black holes stretches light to longer wavelengths, shifting blue light toward red, red toward infrared, and ultimately making all electromagnetic radiation undetectable as it becomes infinitely stretched at the event horizon, effectively disappearing from view. This stretching happens because light climbing out of the black hole's gravitational well loses energy, and since photons can't slow down, they always travel at light speed, they lose energy by increasing their wavelength instead. An observer falling toward a black hole would see the opposite effect. Light from the outside universe would be blue shifted toward higher energies, with the universe appearing to speed up and brighten. The degree of redshift indicates gravitational strength. Measuring redshift from matter orbiting black holes tells us how deep in the gravitational well that matter lies. This effect connects directly to gravitational time dilation, since stretched wavelengths correspond to slowed clocks, two manifestations of the same underlying curvature. Time dilation near black holes means clocks tick more slowly in stronger gravity, an effect that becomes extreme near the event horizon where each second stretches toward infinity from the perspective of distant observers watching the clock approach the boundary. This isn't an illusion or a trick of perception. Time genuinely passes at different rates in different gravitational fields, a fundamental feature of how space-time works in our universe. A clock lowered toward a black hole and then retrieved would show less elapsed time than a clock that remained farther away, having actually experienced less time passage. Astronauts near a black hole would age more slowly than people far from its influence, returning younger than they would have otherwise been had they stayed in weak gravitational fields. This time dilation is the reason the event horizon appears to freeze in falling matter. From outside, infinite time passes during the final approach, though for the infalling observer, only finite time elapses before crossing, both perspectives equally valid descriptions. An hour near a black hole's event horizon could equal years elsewhere, creating situations where time passes at vastly different rates for people at different locations, potentially separating loved ones by decades even though they remain close in space. This extreme time dilation has been dramatized in science fiction, but the effect is real physics, a natural consequence of general relativity's description of how gravity curves time as well as space. The exact ratio depends on how close you are to the event horizon. Closer means more dilation, with the factor growing without bound as you approach the horizon itself. If you could orbit just above the event horizon and then return to Earth, you'd find that far more time had passed for everyone else than for you, potentially centuries or millennia depending on how long you stayed and how close you orbited. This creates possibilities for one-way time travel to the future, aging slowly while the universe ages rapidly around you, though the journey carries obvious risks and no possibility of return. Black holes prove that gravity is geometry, curved space-time itself rather than a force pulling through space, a profound insight that Einstein's theory revealed and that black holes demonstrate in the most extreme possible way. In Newton's theory, gravity was a mysterious force acting instantaneously across distance, but Einstein showed that mass and energy curve the space-time around them, and objects simply follow the straightest possible paths through this curved geometry. Black holes take this principle to its ultimate conclusion, curving space-time so severely that the geometry itself prevents escape, not through forceful pulling but through the structure of possible paths. This geometric view of gravity explains why all objects fall at the same rate regardless of their mass. They're all following the same curved space-time, like different marbles rolling on the same curved surface. Understanding black holes requires thinking about gravity not as a force at all, but as the shape of the universe itself, bent by matter and energy. Stephen Hawking discovered that black holes emit faint radiation, glowing very dimly with thermal energy that leaks out from the event horizon through a quantum mechanical process, surprising the physics community who had believed black holes were perfectly black and emitted absolutely nothing. This radiation is now called Hawking radiation in his honor, representing one of the few insights connecting quantum mechanics and gravity, two theories that remain frustratingly incompatible in most respects. Hawking's calculation showed that black holes have temperature, and anything with temperature must radiate, meaning black holes aren't truly black after all, but instead glow dimly like coals in a fire, though far, far fainter. The discovery suggested that black holes could eventually evaporate completely, disappearing in flashes of radiation given enough time, fundamentally changing our understanding of these objects from eternal prisons to temporary features of the universe. This theoretical breakthrough came entirely from mathematical analysis, years before observational evidence of black holes themselves existed, demonstrating the power of theoretical physics to predict unexpected phenomena. Hawking radiation arises from quantum effects at the event horizon, where the bizarre properties of quantum mechanics create particle pairs from empty space through a process involving the uncertainty principle that governs nature at its smallest scales. According to quantum field theory, empty space isn't truly empty, but constantly seethes with virtual particles, particle-antiparticle pairs that appear and disappear in fractions of a second, normally undetectable because they annihilate each other immediately after forming. Near the event horizon, the intense tidal forces can separate these pairs before they recombine, with one particle falling into the black hole while its partner escapes to infinity, appearing to distant observers as radiation emitted from the black hole. The energy for this radiation comes from the black hole's mass, gradually depleting it as particles escape, meaning black holes slowly lose mass through this quantum evaporation. This process connects the microscopic quantum world with macroscopic black holes, bridging scales that span dozens of orders of magnitude. Virtual particle pairs constantly appear and disappear throughout space, flickering in and out of existence so rapidly that they normally have no measurable effects, existing only for the briefest instants allowed by quantum uncertainty before vanishing back into the vacuum. These quantum fluctuations aren't just theoretical abstractions but have real, measurable consequences, including the Casimir effect, where metal plates in vacuum attract each other due to virtual particle interactions between them. In normal space, virtual particles maintain perfect balance, with particles and antiparticles created and annihilated in pairs that contribute no net energy. The vacuum itself contains tremendous energy in these fluctuations, though we can't extract or use it under normal circumstances. Near black holes, however, the extreme gravitational environment disrupts this balance, allowing the energy of virtual particles to become real through the Hawking radiation process, one of nature's most subtle and remarkable phenomena connecting quantum randomness to gravitational thermodynamics. Near the event horizon, one particle can fall in while its partner escapes, effectively separating the pair permanently and converting virtual particles into real ones through the extreme geometry of space-time at the boundary, allowing energy to appear seemingly from nothing. The particle that falls inward carries negative energy relative to distant observers, which seems strange but is possible inside the horizon where energy measurements become ambiguous and quantum effects dominate. The escaping particle carries positive energy and appears as real radiation to distant detectors, contributing to the glow of Hawking radiation. This separation happens because the intense tidal forces near the horizon pull the virtual pair apart during their brief existence, preventing them from recombining and annihilating as they normally would in flat space-time. The result is that black holes effectively radiate, emitting particles at a temperature inversely proportional to their mass, with smaller black holes being hotter than larger ones, counterintuitive but exactly what the mathematics predicts. This process causes black holes to slowly evaporate over time, losing mass as Hawking radiation carries energy away, gradually shrinking through quantum effects that operate on timescales that dwarf the current age of the universe for any astrophysically relevant black hole. The evaporation is excruciatingly slow for stellar mass and supermassive black holes, with evaporation times measured in 10 to the 67th years or more, far longer than the current universe has existed. However, the process accelerates as the black hole shrinks. Smaller black holes radiate more intensely because they have higher temperature, creating a runaway effect where the final stages of evaporation proceed rapidly. This means black holes aren't eternal. Given sufficient time, they will all eventually disappear in flashes of radiation, returning their mass energy to the universe. The evaporation process connects thermodynamics with quantum mechanics and gravity, suggesting deep relationships between these apparently separate domains of physics, hinting at the underlying unity physicists seek. Smaller black holes evaporate faster than larger ones because their surface gravity is stronger, giving them higher temperatures and causing them to radiate more intensely, according to the relationship Hawking calculated between mass and temperature. A black hole with Earth's mass would have a temperature of mere fractions of a degree above absolute zero, barely radiating at all, while a black hole with the mass of a mountain would glow hot enough to be luminous, radiating powerfully and evaporating in far less than the age of the universe. This inverse relationship between size and temperature seems counterintuitive at first. We usually think of larger things as having more energy, but follows naturally from the physics of curved spacetime and quantum fields. The temperature is inversely proportional to the mass, meaning doubling the mass halves the temperature and reduces radiation by a factor of 16, since radiation scales with the fourth power of temperature. This scaling ensures that astrophysical black holes evaporate incredibly slowly, while hypothetical microscopic black holes would flash out of existence nearly instantly. A black hole with Earth's mass would take longer than the universe's age to evaporate, approximately 10 to the 50 years by some estimates, an almost incomprehensibly long timescale that makes such black holes effectively eternal from any practical perspective. This vast evaporation time arises because Earth-mass black holes have extremely low temperature, mere billionths of a degree above absolute zero, making their Hawking radiation nearly undetectable even if you were right next to them. They radiate so slowly that they actually gain more mass from absorbing cosmic microwave background radiation than they lose to Hawking radiation, meaning they're currently growing rather than shrinking. Only in the far future, when the universe has cooled and expanded so much that background radiation becomes cooler than the black hole's temperature, would evaporation begin in earnest. This demonstrates how weak Hawking radiation is for typical black holes, a theoretical effect that, while important for understanding black hole physics, has negligible practical effects on astrophysical objects we observe today. Supermassive black holes will take 10 to the power of 100 years or more to disappear, timescales so vast they render human intuition completely useless for grasping their magnitude, stretching into eras when the universe will be unrecognizably different from its current state. By the time these black holes begin serious evaporation, all stars will have burned out, galaxies will have dispersed, and the universe will be a cold, dark expanse lit only by the faint glow of evaporating black holes and perhaps the occasional collision of dead stellar remnants. The number 10 to the power of 100 is called a googol, and evaporation times for the largest black holes exceed even this enormous number, reaching into timescales for which we don't have convenient names. During most of this time, the black holes barely shrink, losing mass at rates far slower than they gained it during their active feeding phases. Only in the final trillion years of evaporation does the rate accelerate noticeably, with the last moments proceeding explosively as the black hole's temperature soars and it vanishes in a final burst. As black holes evaporate, they emit more radiation and shrink faster, creating a runaway process in their final stages where the evaporation accelerates dramatically, eventually ending in a bright flash as the last remnants of mass convert to radiation. The acceleration happens because temperature increases as mass decreases, and radiation intensity depends on temperature to the fourth power, meaning small decreases in mass led to large increases in radiation rate. For most of a black hole's evaporation lifetime, it loses mass extremely slowly, barely changing over billions or trillions of years, but the final stages take only seconds or microseconds depending on the final mass. This creates a dramatic end for objects that existed for unimaginable durations, disappearing not with a whimper, but with a bang. The final burst releases the equivalent of millions of nuclear bombs for even modest black holes, though whether any mass remains at the absolute end or whether black holes evaporate completely remains an open question in theoretical physics. The final moments of evaporation release a burst of energy, potentially detectable as a flash of gamma rays if such events occur close enough to Earth, though no such bursts have been definitively identified despite searches. This explosive ending represents the black hole converting its remaining mass entirely to radiation, with the final moments proceeding at relativistic speeds as quantum effects dominate completely. The burst would be brief but intense, potentially brighter than an entire galaxy for the fraction of a second it takes for the black hole to completely disappear. Some theories suggest that tiny primordial black holes from the early universe might be evaporating now, approximately 13.8 billion years after forming, which would make them small enough to complete their evaporation in the current epoch. Detecting such bursts would provide direct evidence for Hawking radiation, confirming this theoretical prediction with observational data and opening new windows into quantum gravity, though none have been conclusively detected despite decades of searching for characteristic signatures. Black holes themselves are invisible, emitting no light from within their event horizons, making them the darkest objects in the universe and impossible to see directly against the blackness of space without surrounding matter to illuminate their presence. This invisibility isn't camouflage or cloaking, but absolute. Light produced inside the event horizon cannot escape, so there's simply nothing to see. No photons that can reach our telescopes from the black hole proper. The blackness of a black hole represents a perfect absence of radiation, darker than any material surface could be, since materials always emit some thermal radiation while black holes trap everything that crosses their boundaries. This invisibility means we can never directly observe the interior or the singularity at the center, fundamentally limiting how much we can learn about these objects. Our knowledge comes entirely from observing matter outside the event horizon as it orbits or falls in, glowing brightly in its final moments before vanishing forever from our view, making black holes cosmic detectives whose clues lie in how they affect their surroundings. We detect black holes by observing their effects on surrounding matter, watching how gas and stars move under the influence of invisible gravitational wells that reveal the presence of these dark objects through orbital dynamics and energetic emissions. When matter falls toward a black hole, it heats up through friction and compression, glowing brilliantly in X-rays and other high-energy radiation before crossing the event horizon. The patterns of this radiation, flickering and flaring as clumps of matter spiral inward, tell us about the black hole's mass and spin rate, properties we can measure despite the black hole itself remaining hidden. Stars orbiting invisible companions also reveal black holes, particularly in binary systems where a visible star circles an unseen partner whose mass exceeds the limit for neutron stars. By measuring the visible star's motion, we can calculate the unseen companion's mass and determine whether it must be a black hole, making black holes detectable through gravitational influence even when they're not actively feeding. Gas falling into black holes heats up and emits X-rays we can detect, glowing with temperatures of millions of degrees as friction converts gravitational potential energy into thermal energy and radiation, making actively feeding black holes among the brightest objects in X-ray astronomy. The heating occurs in the accretion disk, where matter spirals inward in increasingly tight orbits, with inner regions moving faster than outer regions and friction between these differentially rotating layers generating tremendous heat. The hottest material, closest to the black hole, emits primarily X-rays, while cooler outer regions emit visible and infrared light, creating a characteristic spectrum that immediately identifies accreting black holes. X-ray telescopes in space, above Earth's atmosphere which blocks X-rays, have catalogued thousands of black hole candidates by detecting these energetic emissions. The X-ray intensity fluctuates as clumps of gas orbit and fall in, with fluctuation patterns revealing the black hole's mass and spin, providing diagnostic tools for studying these otherwise invisible objects through the death cries of infalling matter. Accretion disks form as matter spirals toward black holes, creating flattened structures of orbiting gas and dust that stretch from near the event horizon outward to distances thousands or millions of times larger, depending on available material and the black hole's feeding rate. These disks arise because matter falling toward black holes typically has angular momentum, causing it to orbit rather than fall straight in, and collisions between particles gradually flatten the material into a disk perpendicular to the rotation axis. Accretion disks are incredibly efficient at converting mass into energy, far more efficient than nuclear fusion in stars, with some disks converting 10% or more of infalling mass directly into radiation before it crosses the event horizon. The inner edge of the accretion disk hovers near the innermost stable circular orbit, the last place where matter can orbit without falling straight in, making this boundary tremendously bright and hot as matter plunges inward from this final stable orbit. These disks can shine brighter than entire galaxies, outshining hundreds of billions of stars combined when supermassive black holes feed voraciously on vast quantities of gas and dust, creating objects called quasars that are visible across most of the observable universe. The incredible brightness comes from the tremendous efficiency of accretion, which converts mass to energy far better than any other natural process, and from the enormous masses involved when supermassive black holes feed at maximum rates. Active galactic nuclei powered by accreting supermassive black holes can generate more energy than all the stars in their host galaxies combined, dominating the electromagnetic output of their galaxies despite the black hole itself being millions of times smaller than the galaxy's extent. This luminosity made quasars detectable at enormous distances, allowing astronomers to study the early universe by observing these brilliant beacons from epochs shortly after the first galaxies formed. The discovery of quasars in the 1960s puzzled astronomers until they realized supermassive black holes could generate such extreme luminosity from relatively compact regions. Jets of particles shoot outward from some black holes at near light speed, extending for thousands or millions of light years beyond the central black hole, forming narrow beams perpendicular to the accretion disk that can dwarf entire galaxies in extent. These jets form through complex interactions between the accretion disk, the black hole's magnetic field, and the rotation of space-time itself, channeling some of the infalling matter's energy outward instead of inward. The jets contain ionized particles accelerated to speeds exceeding 99% of light speed, carrying tremendous energy outward and depositing it in the surrounding intergalactic medium. Where jets collide with surrounding gas, they create giant radio-emitting lobes visible in radio telescopes, sometimes larger than the galaxies that host them. The exact mechanism producing jets remains not fully understood, though rotation appears essential. The fastest spinning black holes produce the most powerful jets, suggesting the jets extract rotational energy from the black hole's spin through the Penrose process or magnetic field interactions. Cygnus X1 was the first black hole candidate discovered in 1964, a powerful X-ray source in the constellation Cygnus, where a blue supergiant star orbits an invisible companion whose mass clearly exceeds the maximum possible for a neutron star. The visible star, designated HDE 226868, circles this unseen partner every 5.6 days, moving at hundreds of kilometers per second, revealing that its companion must weigh at least 15 solar masses. This mass exceeds the theoretical maximum for neutron stars by a substantial margin, leaving a black hole as the only plausible explanation for the invisible companion. The system emits powerful X-rays as gas pulled from the visible star forms an accretion disk around the black hole, heating to millions of degrees before falling in. Stephen Hawking famously bet physicist Kip Thorne that Cygnus X1 wasn't actually a black hole, a bet Hawking later conceded when evidence became overwhelming, acknowledging he'd lost his insurance policy against black holes not existing. Stellar motion near galactic centers reveals the presence of supermassive black holes, with stars moving at thousands of kilometers per second in tight elliptical orbits around apparently empty points in space, tracing out the gravitational influence of invisible massive objects through their precisely measured paths. Astronomers have monitored stars near our galaxy's center for decades, tracking their positions with increasing precision and watching them complete full orbits around Sagittarius, a star, the radio source marking our galaxy's heart. The fastest moving of these stars, designated S2, completes its orbit in just 16 years, reaching speeds exceeding 7,000 kilometers per second at closest approach, fast enough to circle Earth in 6 seconds. Such extreme velocities can only be explained by the presence of an extremely compact, massive object at the orbit's focus. Millions of solar masses concentrated in a region smaller than our solar system. The orbital motions allow precise mass measurements using Kepler's laws, proving that supermassive black holes occupy galactic centers with the same certainty that planetary orbits prove the Sun's mass. Stars orbiting Sagittarius. A star move at thousands of kilometers per second, traveling so fast their motion is perceptible over timescales of months or years despite their enormous distance from Earth, allowing astronomers to track their paths with adaptive optics telescopes that compensate for atmospheric turbulence. These stars follow elliptical orbits just as planets orbit the Sun, but at percentages of light speed, with their closest approaches bringing them within light hours of the event horizon. At such close ranges, the stars experience significant gravitational redshift and time dilation, effects that have been measured and confirmed to match general relativity's predictions. The star S2's closest approach in 2018 allowed unprecedented tests of gravity in extreme fields, verifying that Einstein's theory holds even in the intense gravity near a supermassive black hole. Continued monitoring of these stellar orbits refines our understanding of black hole masses and tests whether any modifications to general relativity are needed in strong field regimes. Gravitational waves are ripples in space-time caused by accelerating masses, spreading outward at the speed of light like waves on a pond, carrying energy away from their sources and slightly stretching and squeezing distances as they pass through space. Einstein predicted gravitational waves in 1916, shortly after completing general relativity, though he thought they would be too weak to ever detect despite transporting real energy across the cosmos. These waves are distortions in the fabric of space-time itself, not vibrations traveling through space, but rather space itself oscillating, alternately stretching and compressing distances perpendicular to the wave's direction of propagation. Only the most violent cosmic events generate detectable gravitational waves, colliding black holes, merging neutron stars, or exploding supernovae, because generating gravitational waves requires enormous masses moving at high speeds with changing acceleration. The waves from even these violent events produce tiny effects, changing distances by less than the width of an atomic nucleus over kilometers, making detection extraordinarily challenging and requiring exquisitely sensitive instruments. LIGO detected gravitational waves from merging black holes in 2015, directly observing ripples in space-time for the first time and opening an entirely new window onto the universe, allowing us to observe phenomena that emit no light. The Laser Interferometer. Gravitational Wave Observatory uses lasers bouncing between mirrors separated by 4 kilometers to detect changes in distance smaller than 1,000th the width of a proton, measuring how gravitational waves squeeze and stretch space itself as they pass through Earth. The first detection, announced in 2016, recorded the final moments as 2 black holes, each about 30 solar masses, spiraled together and merged, releasing 3 solar masses worth of energy as gravitational waves in a fraction of a second. The distinctive chirp pattern, increasing in frequency and amplitude before suddenly cutting off, matched theoretical predictions perfectly, confirming both general relativity's predictions about gravitational waves and the existence of binary black hole systems. This discovery earned the 2017 Nobel Prize and inaugurated gravitational wave astronomy as a new field. This detection confirmed a major prediction of Einstein's theory, validating general relativity's description of gravity as curved spacetime in the most extreme regime yet tested, where black holes collide at significant fractions of light speed. Einstein himself doubted gravitational waves would ever be detected, calling them vanishingly small, and questioning whether they carried real energy or were mere coordinate artifacts. The detection proved that gravitational waves are physical, transporting energy across space and affecting physical objects they encounter, not mathematical illusions or reference frame effects. The observed waveform matched computer simulations based on solving Einstein's equations for colliding black holes, simulations that require supercomputers to calculate because the equations are so complex. Every detail of the signal, its frequency evolution, amplitude, damping time, agreed with general relativity's predictions, providing the strongest validation yet that Einstein's century-old theory correctly describes gravity even in its most violent and extreme manifestations, where space-time itself becomes turbulent. Gravitational waves let us hear black hole collisions across the universe, translating space-time vibrations into audio frequencies that allow us to literally listen to cosmic events, with each collision producing a distinctive sound that rises in pitch before suddenly stopping. The frequency of detected gravitational waves happens to fall in the audio range humans can hear, typically tens to thousands of hertz, making it natural to convert gravitational wave data directly into sound that can be played through speakers. The resulting chirp sounds like a brief whoop or bird call, rising rapidly in pitch and loudness before cutting off abruptly when the black holes merge and settle into a single, quiet hole. Different mass black holes produce different chirp frequencies. Lighter black holes produce higher-pitched chirps, while supermassive black holes create low-frequency waves below human hearing that require space-based detectors. This acoustic translation makes gravitational wave astronomy uniquely accessible to human senses, allowing us to experience directly what happens when black holes merge, hearing across billions of light years and billions of years back in time. The Event Horizon Telescope captured the first black hole image in 2019, photographing the supermassive black hole in galaxy M87 by combining observations from radio telescopes across the entire Earth into an Earth-sized virtual telescope with unprecedented resolving power. The image shows a dark circle surrounded by a bright ring of glowing plasma, exactly matching theoretical predictions for how a black hole's shadow should appear when backlit by an accretion disk. The dark circle is larger than the event horizon itself, representing the photon sphere where light orbits before falling in, creating a shadow about 2.5 times the Schwarzschild radius. Capturing this image required coordinating observations from telescopes on 4 continents, synchronized with atomic clocks to picosecond precision, then combining terabytes of data using sophisticated algorithms that reconstructed the image from incomplete information. The achievement demonstrated both the reality of event horizons and the power of international scientific collaboration, creating an iconic image that will endure as humanity's first direct view of these cosmic phenomena. That image showed the supermassive black hole in galaxy M87, located 55 million light-years away in the Virgo cluster, containing 6.5 billion solar masses and launching a jet visible across thousands of light-years. M87's black hole was chosen as a target because despite its enormous distance, it appears large in the sky due to its tremendous mass, making it one of just 2 black holes that appear large enough to resolve with Earth-sized telescopes. The bright ring in the image shows light emitted by gas swirling at nearly light speed just outside the event horizon, heated to billions of degrees by friction and compression. The ring appears brighter on one side due to relativistic beaming. Gas moving toward us appears brighter than gas moving away, an effect of special relativity at extreme velocities. Subsequent images of Sagittarius A star, our own galaxy's central black hole, confirmed similar structure, demonstrating that the theoretical understanding of black holes matches observations in different mass regimes and galactic environments, and connecting decades of theory to direct observational evidence. Schwarzschild black holes are non-rotating and perfectly spherical, representing the simplest possible black hole solutions to Einstein's equations, characterized completely by their mass alone with no other properties affecting their structure or behavior. Carl Schwarzschild found this solution in 1916, within months of Einstein publishing General Relativity, while serving in the German army and suffering from an illness that would soon kill him. His solution describes eternal, unchanging black holes with perfect spherical symmetry, existing timelessly in empty space without spin or charge, or any distinguishing features beyond mass. Real astrophysical black holes almost certainly rotate, since they form from rotating stars or accumulate rotating material, making Schwarzschild black holes theoretical idealizations rather than realistic models. Nonetheless, the Schwarzschild solution provides crucial insights into black hole physics and serves as the starting point for understanding more complex rotating solutions. Its elegant mathematical simplicity revealed fundamental features like event horizons and singularities, establishing the basic framework all black hole physics builds upon even when rotation and other complications are included. Kerr black holes rotate and are slightly flattened at the poles, bulging at the equator due to centrifugal effects just as rotating stars or planets bulge, creating oblate rather than spherical event horizons with distinct geometry near the rotation axis versus the equator. Roy Kerr discovered the rotating black hole solution in 1963, nearly 50 years after Schwarzschild's work, solving Einstein's equations for black holes with angular momentum. The Kerr solution is far more complex mathematically than the Schwarzschild solution, involving not just one but 2 event horizons and the ergosphere region where space itself rotates. The black hole's spin drags space-time around it, creating frame-dragging effects that force everything near the black hole to rotate in the same direction, unable to remain stationary relative to distant stars. The faster the black hole spins, the more pronounced these effects become, with the maximally rotating black hole having spin angular momentum equal to its mass squared in natural units, representing the fastest possible rotation before centrifugal forces would overcome gravity and tear the hole apart. Reissner-Nordström black holes carry an electric charge possessing net positive or negative charge in addition to mass, creating black holes that exert both gravitational and electromagnetic forces on surrounding particles and radiation. These charged black holes have two event horizons like rotating black holes, with the outer horizon representing the true point of no return, while the inner horizon separates different regions of exotic interior geometry. The mathematical solution for charged black holes, found independently by Hans Reissner and Gunnar Nordström in the late 1910s, shows how electromagnetic charge affects black hole structure, pushing event horizons outward compared to uncharged black holes of the same mass. Extreme charge could theoretically eliminate the event horizon entirely, creating a naked singularity that violates cosmic censorship, though most physicists believe nature prevents such objects from forming. The Reissner-Nordström solution represents another idealized case, probably even rarer in nature than non-rotating black holes, since charge would quickly neutralize through accretion of oppositely charged particles from the surrounding environment. Charged black holes are likely rare since they would attract opposite charges, quickly neutralizing any net charge through accretion of oppositely charged particles from surrounding plasma, dust, and cosmic rays that pervade space throughout galaxies. If a black hole somehow acquired significant positive charge, it would strongly attract electrons while repelling protons, causing negatively charged matter to preferentially fall in until the charge neutralized. The universe contains roughly equal amounts of positive and negative charge in the form of protons and electrons, and since black holes interact with whatever matter surrounds them, maintaining a charge imbalance would be difficult over astronomical timescales. Additionally, charged black holes would radiate electromagnetic energy, losing charge through radiation in addition to neutralization via accretion. These factors suggest that even if charged black holes briefly form, they quickly become effectively neutral, making uncharged or rapidly rotating black holes the dominant types in the universe, with charge playing little role in the black holes we actually observe through their effects on orbiting matter and emitted radiation. Binary black hole systems contain two black holes orbiting each other, slowly spiraling inward as they lose energy to gravitational waves, creating systems doomed to eventual merger when their mutual orbit decays enough to bring them together in catastrophic collision. These binaries form when two massive stars in a binary system both explode as supernovae, leaving behind black holes that remain gravitationally bound, or when two black holes happen to encounter each other in dense star clusters where close passages are common. The two black holes orbit their common center of mass, sometimes for millions or billions of years if their separation is large, all the while emitting gravitational waves that carry away orbital energy. As energy dissipates, the orbits shrink and orbital velocities increase following Kepler's laws, causing the black holes to circle each other faster and faster. The final orbits last mere seconds, with the black holes whipping around each other hundreds of times per second before plunging together and merging in a violent collision that releases tremendous energy as gravitational waves and creates a single, larger black hole that settles into a simple rotating state. These systems gradually spiral inward, releasing gravitational waves that carry away orbital energy and angular momentum at rates that increase dramatically as the black holes get closer together and orbit faster, accelerating the inspiral in a runaway process that ends in merger. The energy loss to gravitational waves is absolutely tiny when black holes are widely separated, making the inspiral imperceptibly slow initially, but it grows as the inverse fifth power of separation, so closer orbits decay much faster. For stellar mass black hole binaries, the early inspiral can last billions of years, with orbital decay proceeding so slowly that thousands of orbits produce barely noticeable changes. But in the final hours, minutes, and seconds, the inspiral accelerates rapidly, with the black holes orbiting each other faster and faster while emitting increasingly powerful gravitational waves. LIGO and other detectors observe only these final moments, the last seconds or minutes when the system radiates most strongly, missing the billions of years of slow approach. The pattern is called a chirp because the gravitational wave frequency increases continuously, rising in pitch like a bird call until the moment of collision. Rogue black holes wander through space, ejected from their original locations by gravitational slingshots during galaxy mergers or asymmetric supernova kicks that give newly formed black holes velocities exceeding their galaxy's escape speed, sending them careening into intergalactic space. When galaxies collide, their central supermassive black holes eventually merge, but if the merger is asymmetric, perhaps because the black holes were spinning in different directions, the final black hole can receive a kick from asymmetric gravitational wave emission, potentially reaching speeds of thousands of kilometers per second. Such speeds can exceed escape velocity even for massive galaxies, ejecting the merged black hole into intergalactic space where it will wander forever, gradually slowing due to friction with intergalactic gas. Stellar mass black holes can also become rogues if supernova explosions are asymmetric, giving the collapsing core a natal kick at birth. These wandering black holes are difficult to detect since they lack surrounding material to illuminate them, making them invisible nomads drifting through the darkness between galaxies, occasional gravitational hazards should anything wander too close. Micro-black holes are theoretical tiny black holes that could exist with masses far less than stellar black holes, potentially ranging from grams to asteroids, existing only if primordial black holes formed in the early universe when conditions allowed collapsed regions at all mass scales. These tiny black holes would have event horizons smaller than atoms or even elementary particles, making them quantum objects where both general relativity and quantum mechanics fully apply simultaneously. If micro-black holes exist, they would evaporate extremely rapidly through Hawking radiation. Black holes with masses less than a small mountain would have already evaporated during the universe's current age. The smallest primordial black holes still existing today would weigh about as much as a large asteroid, with event horizons around a millimeter across, radiating faintly in gamma rays. Despite extensive searches, no convincing evidence for micro-black holes has been found, though they remain theoretically possible remnants from the Big Bang that could, if they exist, even constitute part of dark matter's mysterious mass throughout the cosmos. Some theories suggest microscopic black holes might be created in particle colliders when protons collide at sufficient energy, if extra dimensions of space exist beyond the three we directly experience, lowering the energy threshold for black hole formation from stellar scales to accessible particle physics energies. This possibility generated public concern when the Large Hadron Collider began operations, with some worried it might create black holes that would consume the Earth, though physicists quickly explained why such fears were unfounded. Even if microscopic black holes could form in colliders, they would evaporate essentially instantly through Hawking radiation, existing for only 10 to the minus 27 seconds or less before disappearing in flashes of particles. Cosmic rays far more energetic than collider beams constantly bombard Earth's atmosphere, and if they could create dangerous black holes, the Earth and Moon would have been consumed billions of years ago. No evidence of collider-created black holes has been found, suggesting either they don't form at accessible energies or the extra dimensions required don't exist, making this a speculative possibility rather than observed reality. Such tiny black holes would evaporate almost instantly through Hawking radiation, flashing out of existence in tiny fractions of a second, far too brief to measure directly, releasing their mass energy as sprays of particles that would appear in detectors as unusual particle signatures. A black hole with the Planck mass, the natural mass scale for quantum gravity, would have a lifetime of only the Planck time, about 10 to the minus 43 seconds, making it among the most ephemeral objects imaginable. Even black holes a trillion times more massive would evaporate in nanoseconds, barely long enough for light to cross a millimeter. This rapid evaporation makes primordial micro-black holes observable only if they're massive enough to survive billions of years, yet light enough to be evaporating significantly today. A narrow window around 10 to the 15th grams, roughly the mass of a large mountain compressed to subatomic size. Detecting such evaporating black holes would require catching the gamma-ray bursts from their final moments, distinctive patterns that telescopes have searched for without conclusive results, leaving the question of micro-black holes' existence tantalizingly open. The singularity at a black hole's center is where our known physics breaks down, representing a place our current mathematics cannot describe because infinite quantities appear in equations, usually signaling that the theory has reached its limits rather than describing physical reality. General relativity predicts that at the singularity, space-time curvature becomes infinite and density becomes infinite. Mathematical infinities that physicists believe indicate the theory's incompleteness rather than actual physical infinities in nature. Quantum mechanics typically resolves infinities that appear in classical theories, suggesting that quantum effects must dominate at the singularity, preventing infinite compression and possibly replacing the singularity with some kind of quantum structure we don't yet understand. The singularity represents the greatest remaining mystery at the heart of black holes, a boundary of human knowledge where two of physics' most successful theories, general relativity and quantum mechanics, contradict each other and both admit their inadequacy. Understanding what actually exists at the center requires a theory of quantum gravity, a unified framework that doesn't yet exist despite decades of effort seeking it. At the singularity, matter is compressed to such extreme conditions that describing it as having infinite density likely signals the limitations of our theories rather than physical reality, suggesting that actual black hole centers are described by physics we haven't yet discovered. Infinity appearing in physics equations usually means this model doesn't apply here, rather than literally indicating something infinite, a sign that new physics takes over at the scales involved. At the singularity, densities should exceed the Planck density, where quantum gravitational effects become strong and space-time itself becomes foamy and uncertain, with quantum fluctuations creating a rapidly changing geometry. Some theories suggest the singularity is replaced by a tiny region of extremely dense but finite matter, perhaps supported by quantum pressure effects that general relativity cannot account for. Others propose the singularity is a gateway to other regions of space-time, possibly even other universes, though such ideas remain highly speculative without experimental guidance or mathematical certainty to distinguish possibilities from fantasies. Quantum gravity theories may resolve the singularity's infinite properties by providing new physics that operates at the Planck scale, where quantum uncertainty affects space-time's structure itself, preventing the runaway collapse that classical general relativity predicts should occur. String theory, loop quantum gravity, and other approaches to quantum gravity all predict modifications to general relativity at extreme densities and curvatures, though they disagree on details about what replaces the singularity. Some suggest the singularity becomes a tiny sphere of Planck-scale dimensions rather than a true point, while others propose that quantum effects halt collapse altogether, creating a core region of ultra-dense matter supported by quantum pressure. Unfortunately, testing these ideas observationally appears impossible since anything occurring at the singularity remains hidden behind the event horizon, forever cut off from external observation. The singularity thus represents both a practical and theoretical challenge, practically unobservable and theoretically requiring physics beyond our current understanding, making it perhaps the deepest unsolved problem in gravitational physics, waiting for the quantum gravity breakthrough that will finally reveal what truly hides at black holes' hearts. Inside the event horizon, space and time swap roles in a mathematical sense, with the singularity lying in the future rather than in any spatial direction, making collision with it as inevitable as tomorrow's arrival, rather than like approaching a location you could avoid by changing direction. Outside the horizon, you can move freely in spatial directions but are forced forward in time, unable to reverse time's flow. Inside, this relationship inverts. The radial direction towards the singularity becomes time-like, while time becomes space-like, though these terms become abstract and difficult to interpret physically. This means that preventing yourself from reaching the singularity becomes as impossible as preventing tomorrow from arriving. It's not in front of you in space, but ahead of you in time. All paths through space-time inside the horizon lead to the singularity in your future, just as all paths outside the horizon lead forward in time, with no escape possible because you cannot reverse the direction time flows. This bizarre property makes the black hole interior fundamentally different from anywhere else in the universe, a region where intuitive concepts like motion and destination lose their familiar meanings. Moving forward in time means moving toward the singularity once inside the event horizon, eliminating any possibility of avoiding this destination through spatial maneuvering or accelerating in different directions, since the singularity has become a moment in time rather than a place in space. Just as you cannot avoid tomorrow by moving sideways, you cannot avoid the singularity by changing your trajectory once you've crossed the horizon. The inevitability is absolute and follows from the geometry of space-time itself rather than from any force pushing you toward the center. You could fire rockets, change direction, or try any maneuver imaginable, but all such actions merely alter when you reach the singularity, not whether you reach it. Some paths might delay the encounter by fractions of a second, while others might hasten it, but none lead anywhere else. This transformation of the singularity from spatial location to temporal inevitability represents one of black holes' most profound and disorienting features, challenging our everyday understanding of causality and possibility, showing how extreme gravity reshapes reality's basic structure. The interior of a black hole remains one of physics' deepest mysteries, a region we can theorize about but never observe, forever hidden behind the event horizon that prevents any information from escaping to tell us what actually happens inside. Everything we know about black hole interiors comes from mathematical extrapolation of general relativity's equations, assuming they remain valid even at the extreme curvatures inside the horizon. But since these equations themselves admit they break down at the singularity, our confidence in their predictions decreases as we consider regions closer to the center. No experiment can test what actually happens inside because any probe we send crosses the horizon and cannot return information about its findings. This makes the interior fundamentally different from other physical systems, not merely unobserved but unobservable in principle, separated from our universe by a causal boundary that no signal can cross. We're left with educated guesses guided by mathematics, but no empirical check on whether our theories correctly describe this hidden realm where extreme gravity meets quantum effects in ways we don't fully understand yet. Ring singularities may exist inside rotating black holes instead of point singularities, forming closed curves where matter collapses to infinite density, creating donut-shaped regions of breakdown in space-time rather than infinitely small points at the center. The Kerr solution for rotating black holes predicts such ring singularities, with the ring lying in the equatorial plane and having a radius related to the black hole's angular momentum. This geometry creates even stranger interior properties than non-rotating black holes, with the mathematical solution containing regions where closed time-like curves exist, theoretical paths through space-time that loop back to their own past, potentially permitting time travel. Most physicists believe such paths are either inaccessible or rendered impossible by quantum effects that aren't included in classical general relativity, though the mathematics clearly shows them in the idealized solution. The ring structure might also be an artifact of assuming perfect eternal rotation in empty space, with realistic black holes forming from collapsing matter perhaps having different interior structures that modify or eliminate the ring singularity entirely through quantum effects. Mathematical wormholes could theoretically connect black holes to other regions of spacetime, creating tunnels through higher dimensional space that link distant locations or even different universes, providing shortcuts between places that would otherwise be separated by vast distances through normal space. The mathematical solutions for wormholes exist within general relativity, arising naturally from the equations that describe black hole geometry when extended in certain ways. However, these solutions require exotic matter with negative energy density to hold the wormhole's throat open and prevent it from collapsing, and no known form of matter has such properties in the quantities required. Without exotic matter, any wormhole would pinch off faster than light could traverse it, making travel impossible even if the structure briefly formed. The Schwarzschild black hole solution, when maximally extended, contains a wormhole structure connecting to a white hole in another region of spacetime, though this feature almost certainly doesn't exist in realistic black holes that form from stellar collapse rather than existing eternally. Wormholes remain fascinating theoretical constructs, but probably not actual features of black holes in nature. Traversable wormholes likely require exotic matter that may not exist, substances with negative energy density that would violate the usual energy conditions assumed in classical physics, making such matter purely hypothetical unless quantum effects permit temporary violations. The Casimir effect demonstrates that quantum fields can briefly have negative energy densities in small regions between closely spaced conducting plates, though whether such effects could be amplified to macroscopic scales needed for wormholes remains unknown and doubtful. Even if exotic matter exists, stabilizing a wormhole would require enormous quantities of it, possibly more mass-energy equivalent than exists in entire galaxies, making traversable wormholes impractical even if theoretically possible. Some theories propose using advanced civilizations' technology to manipulate space-time and create wormholes artificially, though such speculations venture far beyond current physics into science fiction territory. Natural traversable wormholes almost certainly don't exist, and artificial ones would require technology so advanced that contemplating them now is like ancient Greeks trying to imagine smartphones, separated not just by technological capability, but by fundamental understanding of nature's possibilities and limits. The Penrose process can extract energy from rotating black holes by exploiting the ergosphere's properties, where particles entering this region can split in ways that allow one particle to fall into the black hole with negative energy, while the other escapes with more energy than the original particle possessed. This seemingly paradoxical process works because inside the ergosphere, particles can have negative energy relative to distant observers while still moving forward in time from their own perspective, an allowed circumstance in the exotic geometry of rotating black hole spacetimes. The escaping particle carries away energy that ultimately comes from the black hole's rotational energy, gradually slowing the black hole's spin and extracting mass energy that can be harnessed. In principle, up to 29% of a maximally rotating black hole's mass energy could be extracted through repeated Penrose processes, vastly more than nuclear fusion, which releases less than 1% of mass energy. Advanced civilizations might use the Penrose process to harvest energy from supermassive black holes, creating power sources that dwarf stars, though human technology remains billions of years from such capabilities even if the process proves practically feasible. Black holes shape galaxy formation and evolution throughout cosmic history, with supermassive black holes regulating star formation in their host galaxies by heating and ejecting gas that would otherwise collapse into stars, creating a feedback loop that connects galactic and black hole growth. Jets and winds from actively feeding black holes pump energy into surrounding gas, heating it enough to prevent cooling and collapse, effectively shutting down star formation in the galaxy's central regions. This feedback explains why the most massive galaxies contain relatively few young stars despite having enormous gas reservoirs. Their central black holes have become so massive and energetic that they've blown away or heated the gas needed for star formation. Without black hole feedback, theoretical models predict galaxies would form far too many stars too quickly, contradicting observations of actual galaxies, stellar populations, and star formation histories. The remarkable correlation between supermassive black hole masses and properties of their host galaxy's bulge suggests the two grow together through a self-regulating process, where black hole activity and galaxy evolution influence each other over billions of years, creating the diverse population of galaxies we observe throughout cosmic time. The mass of a galaxy's central black hole correlates with the galaxy's properties, specifically with the mass of the galactic bulge and the stellar velocity dispersion, a relationship called the M-sigma relation that reveals deep connections between black holes and galaxies despite their enormous size differences. More massive galaxy bulges contain more massive black holes, with the black hole typically containing about 0.5% of the bulge's stellar mass. This tight correlation suggests that black holes and galaxies don't grow independently but through linked processes where each influences the other's development. Mergers between galaxies also merge their central black holes, building more massive black holes while simultaneously building more massive galaxy bulges through star formation triggered by the collision. The correlation extends across 7 orders of magnitude in mass, from dwarf galaxies with 1,000 solar mass black holes to giant ellipticals with billion solar mass monsters, suggesting the relationship represents a fundamental principle of cosmic structure formation rather than coincidence. Understanding why this relationship exists and how it arose requires understanding both galaxy formation and black hole growth throughout cosmic history, connecting the largest and smallest mass scales involved in structure formation. Quasars are supermassive black holes actively consuming vast amounts of matter, shining so brilliantly they outshine their entire host galaxies by factors of hundreds or thousands, making them the most luminous persistent objects in the universe visible across most of cosmic time. The name quasar comes from quasi-stellar radio source, coined when these objects were first discovered in the 1960s as bright point-like sources that appeared star-like but emitted radio waves and had peculiar spectra. Their true nature became clear when astronomers measured their distances using redshifts. They were billions of light years away. meaning their apparent brightness implied intrinsic luminosities exceeding entire galaxies despite compact sizes. Only supermassive black holes feeding at enormous rates could generate such extreme luminosity from relatively compact regions. Quasars were most common when the universe was a few billion years old, during an era of intense galaxy formation and mergers that funneled gas towards central black holes, allowing them to feed voraciously. Modern quasars are rarer because galaxies have exhausted or ejected much of their central gas, leaving black holes largely dormant except during occasional feeding events when new gas becomes available. These ancient objects were more common in the early universe when galaxies formed rapidly and merged frequently, creating conditions that fed supermassive black holes with prodigious quantities of gas and triggered intense accretion that powered the brightest quasars billions of light-years away. The quasar era peaked when the universe was about 3 billion years old, roughly a quarter its current age, when galaxy formation rates were highest and mergers were common. During this cosmic epoch, many galaxies hosted actively feeding supermassive black holes that shone as brilliant quasars, with accretion disks radiating across the electromagnetic spectrum from radio waves to gamma rays. As the universe aged, galaxy mergers became less frequent and gas supplies dwindled as stars formed and supernova explosions heated and ejected gas from galactic centers, gradually starving black holes and causing quasar activity to decline. Today, bright quasars are much rarer, with most supermassive black holes feeding at far lower rates or remaining dormant, occasionally flickering to life when gas clouds or disrupted stars provide fresh material, showing that cosmic history's most active phase of black hole growth has largely passed. Black hole mergers are among the most energetic events in the cosmos, releasing more energy in seconds than the Sun will emit in its entire 10 billion year lifetime, converting several solar masses of matter directly into gravitational wave energy during the final moments of collision. When two black holes merge, the final plunge and ring down occur in fractions of a second, with the black holes orbiting each other hundreds of times per second before combining. During this brief period, they radiate gravitational waves with power that can briefly exceed all the electromagnetic radiation in the entire visible universe combined, though this energy emerges as invisible ripples in space-time rather than light. The violence of these mergers deforms the resulting black hole, causing it to vibrate like a ringing bell in the ring-down phase, emitting gravitational waves at characteristic frequencies determined by the final mass and spin. These merger events provide unique laboratories for testing general relativity in its most extreme regime, where space-time itself becomes dynamically turbulent and predictions must be computed numerically using supercomputers to solve Einstein's equations in their full nonlinear glory, creating tests that general relativity has passed with flying colors. Tidal disruption events occur when stars wander too close to black holes, torn apart by tidal forces before crossing the event horizon, with different parts of the star feeling such different gravitational pulls that the star stretches and breaks apart like taffy. These events happen when a star's orbit brings it within the tidal radius, the distance where tidal forces exceed the star's self-gravity, typically several times larger than the event horizon for supermassive black holes. The star doesn't fall in intact, but instead shreds into a stream of gas, with some material gaining enough energy to escape while the rest remains bound to the black hole and accretes over months to years. The debris stream wraps around the black hole multiple times before settling into an accretion disk, creating a temporary brightening called a tidal disruption flare that astronomers can observe across millions of light years. These events occur relatively rarely, perhaps 1 per 10,000 years per galaxy, but provide valuable information about supermassive black holes in otherwise dormant galaxies where accretion rates are normally too low to detect, essentially lighting up invisible black holes temporarily when a star ventures too close. Half the star is consumed while the other half is flung into space at tremendous speeds, with debris from the disrupted star acquiring velocities of thousands of kilometers per second, sometimes exceeding the galaxy's escape velocity and becoming unbound forever. The asymmetry arises from how tidal forces affect different parts of the star. The leading edge experiences stronger gravity than the trailing edge, creating a velocity gradient that both stretches the star and accelerates different portions differently. Some stellar material gains energy and achieves hyperbolic orbits that carry it away from the black hole and out of the galaxy, while other material loses energy and falls into tightly bound elliptical orbits. orbits that return repeatedly to pericenter, gradually circularizing through collisions into an accretion disk. The consumed portion provides a temporary feast for the black hole, brightening it across multiple wavelengths from X-rays to optical light as the accretion rate temporarily spikes. Meanwhile, the ejected material escapes to intergalactic space, enriching the circumgalactic and intergalactic medium with processed elements from the star's interior, redistributing matter that might otherwise have remained in the galaxy for billions of years. Black holes may eventually be the last objects remaining in a cold, dark universe, persisting long after stars have burned out, galaxies have dispersed, and protons themselves have potentially decayed, outlasting virtually every other cosmic structure through the unimaginably distant future. In cosmological models of the far future, the universe continues expanding indefinitely, spreading matter so thin that new star formation eventually becomes impossible as galaxies exhaust their gas supplies. After all stars die, typically within 1 trillion years or so, galaxies contain only stellar remnants, white dwarfs, neutron stars, and black holes, with black holes being the most durable. Even planetary orbits decay through gravitational wave emission, causing Earth-like worlds to spiral into remnant stars over timescales of 10 to the 20 years, though black holes remain stable far longer. If protons decay, as some theories suggest with lifetimes around 10 to the 36th years, even white dwarfs and neutron stars would eventually evaporate, leaving only black holes as gravitationally bound objects. These black holes would then evaporate via Hawking radiation over periods exceeding 10 to the 100 years, creating an era where the universe's only significant structures are evaporating black holes, gradually returning their mass energy to space as radiation. In the far future, black hole evaporation might be the universe's final source of energy, providing the only significant energy release in an otherwise maximally entropic cosmos where all other energy sources have been exhausted and temperature differences have vanished through expansion. As black holes evaporate, they convert their mass to radiation, creating local deviations from thermodynamic equilibrium in the otherwise dark, cold universe. Hypothetical advanced civilizations might gather near evaporating black holes to harvest this energy, using it to power computation or whatever activities sentient beings might pursue in that distant era. The radiation from evaporating black holes would be the last significant energy flow in the universe, a slow drip of power in a sea of near absolute zero background. Eventually, even this source would exhaust as the last black holes evaporate, leaving the universe in a final state of maximum entropy, the heat death, where no energy flows remain and nothing interesting can occur, no computation, no life, no change, just an eternal, cold, dark equilibrium stretching infinitely into the future with no possibility of reversal. Black holes connect our largest cosmic structures to the smallest quantum realms, existing at the intersection where gravity becomes so strong that quantum effects cannot be ignored, forcing physicists to confront the incompatibility between general relativity and quantum mechanics. At event horizons and singularities, both theories claim validity but produce contradictory predictions, creating the unsolved mystery of quantum gravity that represents physics' deepest challenge. Hawking radiation demonstrates that black holes have temperature and entropy, properties usually associated with systems of many particles rather than space-time geometry, suggesting deep connections between thermodynamics, information theory, and gravity. The holographic principle, inspired by black hole thermodynamics, proposes that all information in a volume of space can be encoded on its boundary, hinting that space-time itself might emerge from more fundamental quantum information. Black holes thus serve as theoretical laboratories where humanity's two greatest physics frameworks meet, revealing their limitations and pointing toward the deeper theory that must someday unify them, connecting the cosmic and quantum in ways we're only beginning to glimpse through mathematics, awaiting experimental clues or revolutionary insights that will finally solve the mystery at their hearts. We've journeyed together through the profound darkness of black holes, exploring these cosmic enigmas from their violent births to their eventual evaporation in the unimaginably distant future. These objects represent the universe at its most extreme, where our understanding reaches its limits and mystery still dwells. As you drift towards sleep tonight, let these cosmic wonders remind you that even in the deepest darkness, there is structure, order, and beauty waiting to be discovered. Rest peacefully, knowing the universe continues its ancient dance through space and time.